Okay, I think I'm recording. You should see a red button that indicates that I'm recording.
Okay, very good. So I start now.
Yeah, please.
Okay, so let me first thank you, Denjo, and everyone else for inviting me to this seminar. It's a new format, and it's interesting that I get to talk to such a widely dispersed group of people. And as the title indicates, I'm going to talk to you about entanglement in the quantum Hall system and a generalized Chern-Simons form. So let me start by explaining what the problem is. The quantum Hall effect, as we all know, is a very interesting and important thing. Over the last 35 years or so, it has produced a lot of different results, interesting both mathematically and from the physics point of view. And what we want to do is to look at entanglement in the quantum Hall system. So the physical setup to begin with is like a two-dimensional surface. There is a number of electrons here in 2 dimensions. We have a perpendicular magnetic field. So the states, the eigenstates of the Hamiltonian would be the so-called Landau levels. And we want to look at a state where you saturate, say, one of the Landau levels, say the lowest Landau level, if you like. So this two-dimensional picture that I have here, it's essentially saturated with electrons. And then we draw some closed curve, like the dash curve shown here. And we ask, what is the entanglement between states inside and outside? That is the basic question. We will, of course, generalize to higher dimensions as well, but this is sort of the framework of what we want to talk about. Now, you might ask, why is this interesting? What is the motivation to do that? Well, it's interesting because quantum Hall effect is an interesting physical effect, and many, many different facets of it are interesting for different reasons. So one might say, yes, this is an interesting question, even just in the limited physical context of quantum Hall effect. But there is also a larger framework in which you can view this, and that has to do with non-commutative geometry and gravity. And to motivate that, let me just make 3-4 different points here. First of all, entanglement is an intrinsic property of relativistic quantum field theory. Secondly, Einstein gravity, we know, can be related to entanglement entropy. Now, if we want to think about it in the language of non-commutative geometry, in non-commutative geometry, we attribute quantum degrees of freedom to space itself. In describing a fuzzy or non-commutative manifold in terms of a Hilbert space of states, we are attributing degrees of freedom to space itself. So when we try to use the lowest Landau level as a model for a fuzzy space or a non-commutative version of space, entanglement in this quantum Hall system is effectively talking about entanglement for states which define space itself. And that would be interesting because it can, via the entanglement entropy from here, we may hope to relate it back to Einstein gravity through this second point here. So these are kind of the general motivations for it. And to begin with, I want to explain what I'm hoping to find. So the key question we want to ask is, how does the entanglement entropy for the Hall system depend on background fields, specifically gauge fields and the spin connection? So going back to this picture, I mentioned the magnetic field. You can change the magnetic field and ask, how does the entanglement respond to that? Or you can put this on a curved manifold. You have the spin connection. You can change the spin connection and ask, how does the entanglement entropy change? So this is one of the key questions. And I also want to look at some other properties of entanglement in the Hall system in comparison to ideas from relativistic field theory. Okay, so that's a basic theme of this seminar. Before we get into the details, though, I want to tell you a little bit about the two main results that I'm aiming for, so that in the midst of technical details, one may not see clearly what we are going for. So let me say this now. So what we are going to find are two different results. First, the dependence on the background fields I want to show is related to a generalized Chern-Simons form. And in particular, that Chern-Simons form is associated to what is called the Dolbeault index density. Secondly, we will define a modular operator for this problem and show that its spectrum is actually R+. These are the two basic results. Where the first one is an eminently physical result. The second one is a mathematical property, which I think is important or interesting, but I'm not quite sure what the implications are of this second result. If you want to look up more details in a paper, the relevant article is this archive number from here. That's January of this year. Earlier papers can be traced from this, and some of the work I'm reporting on is in collaboration with Dimitra Karabla. Okay, so let me first recall to you what I'm going to talk about now is familiar to most of you. I just want to recall a few items so that when we talk about Hall effect, we can relate back to things here. So we are looking at relativistic quantum field theory. So we know that local operators should commute at space-like separations. So phi x, phi y, where phi is any operator, not necessarily a fundamental field operator. At separation which is space-like, they commute. In some neighborhood of space, I can define a local algebra of observables by looking at bounded operators of this form, where f is some test function which has support in the region O. So these are local operators. And if O prime is causally disconnected to O, so it's in the causal complement, so to speak, then the operators in O prime commute. Yeah, that's the same as this statement up here, basically. And we can take, therefore, AO prime to be contained in the set of operators which commute with AO. In fact, we can take it to be the full commutant. Everything that commutes with AO is AO prime. And this is something that goes back to Haug, which tells us that if I take a double commutant, namely, I do it one more time, start with O prime and go back, I get the same algebra I started with. So this tells us that these algebras are really von Neumann algebras. If you like, that's one way to define the von Neumann algebra. Let's go on a bit and look at some of the implications. Is there a question? No. Okay. While we can define local algebras, we know very well that states do not factorize into local states. A simple way to see that, which I find quite fascinating, is just try to define what you might call local single particle states by taking a creation operator, act on the vacuum, put a test function that has support in some region, do a similar thing with another test function, and let's say that support for these two functions are disjoint and space-like separate. Okay, so these are two local particles defined, one over here, one over there. The overlap is trivial to calculate in a free field theory, looks like this. The key observation here is the omega k in the denominator, which is needed for relativistic invariance. If I look at the non-relativistic limit, where omega k is replaced just by the mass, this integration over k gives you a delta function. Overlap of f and h is 0, therefore this integral becomes 0. But in a relativistic theory, where omega has this k dependence at high k, this is no longer 0, which tells us that there is correlation of these functions over long distances, even at space-like separation, which tells us that we cannot really define local single particle states. That's just one example of how factorization of states would fail. So entanglement, therefore, we have to conclude, is a key characteristic feature of relativistic field theory. Of course, another interesting observation is that if you start from the vacuum state, a local algebra is sufficient to generate a dense set of states for the full Hilbert space. Now, let me say a couple of things more about this before we go on to the Hall effect. An important observation regarding these algebras in O and O prime is that if you have a state psi, we can define an anti-linear map which takes operators A and turn them into A dagger, like so, okay, in terms of their action on a state. And this anti-linear operator, very often called the tomato operator, squares to 1. And in terms of this operator, we can define S dagger S to be delta. That's a modular operator. Okay, so what I'm saying really is that this S operator, while it's an anti-linear operator turning A to A dagger, it's not unimodular. It changes the norm. A psi and A dagger psi don't necessarily have the same norm. So if you want to take this S and pick out the unimodular part and the modulus part, roughly speaking, the modulus part is delta. And the unimodular part is a conjugation that is called the tomato conjugation that relates A and A prime. But that part is not so important for us. The modular operator is something I'll come back to. The reason why this is interesting, of course, is that different types of von Neumann algebras can be characterized by the spectrum of delta. Okay, that's Alan Cohn's result. And so studying the spectrum of delta tells us something about the algebra. In the specific context of relativistic field theory, I mean, this part I talked about earlier in this slide, that's for any kind of von Neumann algebra, given certain conditions, of course. But in the specific context of relativistic field theory, the relevant von Neumann algebra is supposed to be so-called hyperfinite type 3-1. What that really means is that if I look at the spectrum of delta, the modular operator, and take the intersection over all possible choices of the state psi, the spectrum should be R plus. Okay. So this is one of the things we might try to ask, is this true when I come to quantum Hall effect? And one other observation is that for the type 3-1 algebra, essentially there are no unentangled states. There's a theorem by Alan Cohn and Sturmer, which says by unitary transformations defined separately in A and A prime, one can bring any state arbitrarily close to any other state, essentially ruling out unentangled states because the vacuum suddenly is entangled and I can bring any state close enough to that. Okay, so that's just some factoids, if you like, from relativistic field theory that we just want to keep in mind when we go into the analysis of the Hall system. So what I'm going to do now is to talk really about Hall effect and ask, what is it about entanglement that we can say? So to be very specific, I'm going to start by considering quantum Hall system on a two-sphere. We regard two-sphere as SU2 mod U1. What this tells us, of course, is that the curvatures here, namely the curvature on S2, takes values in the algebra of U1. So it's a U1 valued curvature. And I can put magnetic fields proportional to that on the two-sphere. I can coordinatize the two-sphere by SU2 elements, modulo U1, of course. So spatial derivatives on S2 will correspond to translations in the group. I choose them to be right translations. Let's say R plus R minus, where R acts on this SU2 matrix element by generators appearing on the right translations. These are the standard generators of SU2 in some normalization. So we want to consider a uniform magnetic field proportional to the curvature, which is this U1 valued curvature, which is of course constant in a suitable basis. So we can make a constant magnetic field on the two-sphere. And because the translation operator is R plus R minus commuted to R3, a la SU2 algebra, we see that since the commutator covariant derivatives must be the magnetic field, R3 value must specify the magnetic field. So it is then fairly straightforward to calculate wave functions and so on for this problem. Okay. Let's say, to be specific, we take the Hamiltonian to be just the Laplacian, R plus R minus acting on psi. These are some scale factors. Little r is like the radius of the sphere, if you want to think of it being embedded in 3 dimensions or things of that sort. So I have this Hamiltonian operator. I have to look at states which obey this condition where R3 specifies the magnetic field. So easy enough to do because you're looking at functions on SU2, modular a condition that its R3 value must be fixed. So therefore, the wave functions are simply given by these Wigner functions, which are matrices in different representations corresponding to the SU2 element. In this way of writing, the states on the left are freely choosable. On the right side, I have specified W that picks this to be the lowest, I mean, not necessarily lowest, it picks it to be a specific state for which the R3 value is fixed. We have to, of course, take it to be half an integer. So minus n over 2, n is quantized. It's related to the magnetic field like so. And quantization of n, of course, is the standard direct quantization. So we know the wave functions trivially from just looking at the SU2 algebra. The fermion field operator, therefore, if I go back here, look at this eigenvalue equation and solve it, the fermion field operators I can express in terms of some annihilation operators A, wave functions. This is for the lowest Landau level, similar expressions for the high Landau levels also. Okay. And A sub S, I can obtain from the field operator psi by just the inversion formula. US and US star and US are the one particle wave functions of the lowest Landau level here. So I can construct A and A dagger from there. Now, what are these one particle wave functions? We will need a specific form when we get into the discussion of entanglement. These are easy enough to do. For the lowest case, lowest Landau level, the right side here is in fact a lowest weight state, or highest weight state. So in that case, there is a holomorphicity condition that is obeyed, namely R minus on such states would be 0. And one can solve it trivially in a parameterization of the two sphere. In terms of stereographic coordinates Z and Z bar, I can write the wave functions explicitly like so. So there are little n plus 1 states. S is an index taking values 0 to n. And they obey this holomorphicity condition. So what is the state we are interested in, the multi-particle state? We want to look at the fully filled Landau level, which means the state of interest is I start with a vacuum, I put in a creation operator for every one of these states. That's a fully filled lowest Landau level, nu equal to 1. So this is the state that we are looking at. Okay, now we consider taking the sphere and dividing it into two regions. For simplicity, I'm going to start by dividing it along the equator, which means that ZZ bar is R square equal to 1. That corresponds to the equator. Okay. So what I'm going to do is to go back to these formulae here and notice that I'm integrating over the entire sphere here. By restricting the integration to the north and south hemispheres, I can define partial integrations here, and they correspond to what we might call local operators. Okay, so B sub S is just go over the northern hemisphere from 0 to z equals 1. C sub S is over the southern hemisphere, and these are local. You can think of the integration being restricted here as if it's a local test function that I'm putting here. And let me define lambda S to be the integral up to the equator over the northern hemisphere. Now, the important reason why this separation is useful is that B and B dagger and C and C dagger form two independent fermionic algebras. And my original operator, A and A dagger, can be written in terms of B and C like so. So effectively, at the operator level, we are trying to get a separation of my original set of operators into local operators defined in each region. Now, we can do linear transformations on BB dagger or on CC dagger, like so. These transformations correspond to local observables, so to speak, because the B's are essentially restricted to the northern hemisphere, and these transformations, therefore, are like a local algebra A, and the V's here would be like A prime. Okay, so we have a kind of a framework and a setup similar to what we wanted to do, or wanted to think about in quantum field theory. Okay, let's go on. Let's look at the occupied single particle state. So I'm going to take this A dagger from here, but A dagger now I can write in terms of B's and C's like so. Apply on the vacuum. Here is my one particle state for one particular wave function or one particular state inside the lowest lambda level being occupied. Now, of course, I had to take the product over all of them because recall that my real many-body state is this one. So I had to put A's in the split form for each of them and work out what it looks like. And once I do that, I can define two reduced density matrices. Rho sub B means I'm basically tracing over the C's and the C daggers, these guys, which are operators in the southern hemisphere. And in rho sub C, I trace over the B's and get something defined in the southern hemisphere. Okay, so these are two local reduced density operators that I get. And the procedure I'm following here essentially was used by DeBail, Reed, and Razai, and also something similar has been used by Rodriguez and Sierra in the quantum Hall system. Okay, they were looking at just two-dimensional quantum systems and just a flat situation. The important thing is that once I have these reduced density matrices, I can write down the von-Neumann entropy, which I can call the entanglement entropy in this context. And that would be just sum over all states of this combination here, lambda log lambda, and 1 minus lambda log 1 minus lambda. And you can sort of see them coming out of these terms in the reduced density matrices. Okay, so this is the quantity of interest. And if you think about it a bit more, you can sort of see how this is going to look like. Recall that the wave functions have this structure. So when I look at u star u, I'll get a z bar z to some power upstairs, and then there is, of course, this denominator. So it starts around 0. For any non-zero s, it starts at 0 when z is equal to 0, which is the North Pole. Then it starts building up. Then when you go to large z, it goes down again. So there is a peak in u star u following from this expression. That peak for small values of s will lie in the northern hemisphere near the North Pole. And for large values of s, it will lie near the South Pole. Okay? That means that lambda s is nearly 1 for small s, and lambda s is nearly 0 for large s, meaning that either limit, the contribution to the entropy is very small. The dominant contributions to S will arise from the transition region, which is near the equator, where you have lambda in some kind of middle value for S, where lambda is approximately half. Okay, so for that reason, the entanglement entropy becomes concentrated around the equator, and it can be calculated is proportional to some UV cutoff and is proportional to what you might call the area of the interface, which is in this case just the circumference of the equator. I'm not going to go into the detailed calculation of this. There are more details, including high dimensional cases, in a forthcoming paper by Dimitra. What I want to do is to ask the question: how do these lambdas depend? These lambdas, which go into the computation of the entanglement entropy, how do they depend on background fields such as gauge fields and spin connection? If I change the background fields, how do they respond? Well, it's a straightforward question in many ways. You can answer it also in several different ways. One way is to say, well, here is my Hamiltonian. This is what I'm trying to solve. I change the background fields. I can simply say the Hamiltonian is altered, do perturbation theory, compute the change in the states, and I should simply be able to figure out what this is. That's one way to do that, and we can do it up to a certain order. Another way is what I'm going to outline here. But at the outset, let me say that all these different ways are going to give you the same answer. So it's just different ways, they illustrate different facets of the problem. So let me talk about how we might compute it in another way. And for this, instead of saying we'll start with the all states occupied, let's first look at the situation where M states are occupied. Okay, the first M states are occupied. So it's a partially occupied lambda level. So you can specify that by saying that there is an occupancy matrix, which has an m by m identity matrix, and the rest of these states have zero occupancy, so all these are zeros. Okay, so this is an n plus 1 by n plus 1 matrix, where n is that little n I showed you here. This, remember, little n plus 1 is the number of states. So we look at the occupancy matrix. Now, when I look at large values of n, one way to analyze matrices or things related to matrix algebra is to look at the classical function corresponding to that. If I give a matrix, I can take the matrix elements, multiply by the one particle functions u and u star, and create a classical function. And that classical function is the so-called symbol for the operator or the matrix, symbol for the matrix. Strictly speaking, it's what's called a covariance symbol. In this case, it's trivial to write down. You take this identity matrix, m states are occupied. So here is the symbol for that. Okay, I go 0 to m minus 1, u star u. That's a classical function corresponding to this matrix. So if I take this object, look at the classical function, and take the difference between m and m minus 1, that's exactly u star u for the mth state. And I am interested in the gauge field dependence and spin connection dependence of this quantity. So that means if I know how to calculate these functions, I can pull that out, pull that information out. How do I calculate the functions? The simplest way to do that is, rather than look at P naught by itself, multiply by some other function, some other matrix A naught. Call it A naught because it looks a little bit similar to the time component of a gauge field. Calculate this object and take the difference. This is exactly the kind of calculation you do when you do effective Hamiltonians or effective actions or droplets in quantum Hall systems. That's why I'm phrasing it in this language. Of course, there is a trace over two operators here. If you write it out in terms of classical functions, there'll be star products involved, but the leading term will have no star product. And if I take the variation of this f with respect to A naught, I pull out the term I want, which is this. Okay, and there are some star product fractions. So the question is, how do I calculate this? And I'm going to outline one way to do that and a different way later. So let's just look at U1 fields on, say, CPK. I'm going to present the more general result now. I'll discuss details of CPK later, but let's assume for the moment that we're going to do this on CPK. So what we are saying then is that there is a Kähler-2 form on this manifold. My background magnetic field is proportional to the Kähler-2 form. It's a multiple of the Kähler form. Let me write the magnetic field therefore as D of some Kähler-1 form or something proportional to Kähler-1 form, which I call little a. Okay, so that's my background magnetic field. That serves as the symplectic structure when I quantize, and the states in the Hilbert space which follow from this symplectic structure, those are exactly the lowest Landau level states. Okay. Their lowest Landau level, I can do a kind of a holomorphic quantization and get all the states from here. So now imagine I'm shifting the background magnetic field, I'm changing it. So I'm going from little a to little a plus capital A, some correction. And that's equivalent to changing omega to omega plus f, omega plus dA, omega plus f. So what we are trying to do then, going back here, is to calculate this object P naught A naught with a background omega plus f. Now, what we can do is to rewrite as a trace with omega or as an integral with with omega without the f. But the price you pay for that is A naught must be replaced by some script A. Once I bring it to this form, I can expand it in terms of star products. It'll look like this. The leading term is all I need. Which one? Which is this term. And therefore, the whole issue boils down to the following thing. If I start with omega plus f, can I calculate script A? If I do, then I have the answer. I just take the variation with respect to A naught, and that gives me the quantity of interest from what we said here, namely this observation. Okay, so how do we do that? Well, omega and omega plus f should belong to the same topological class, otherwise this is not going to work. But of course, we are considering perturbation, so that is acceptable. So the idea here is that I can do a diffeomorphism on the classical phase space, not a canonical transformation, but a diffeomorphism, and map omega plus f to omega. It involves a change of coordinates like so, v goes to v minus w. And of course, when that happens, you have to change a naught, because a naught is now evaluated as v minus w, and that's your script A. Okay, so the idea is find a diffeomorphism w such that omega plus f maps to omega, and then use the diffeomorphism to calculate script A. Okay. Written in terms of the one forms, the difference should be just d of theta, so that the omegas obey this structure here. Okay, when I take the derivative, I eliminate theta and get this equation. So this is kind of the thing that one does in the context of Moses' lemma in classical mechanics. So I'm simply using that here. And let's go on to this. I'm going to show you a transparency, which is a little bit dense. I apologize for that, but we don't need all the details. You don't need to remember that there is a sub one here or a script m here or anything of that. So the point I want to make is simply this. Let's write down this equation here in terms of little a and big A. Write this equation down in terms of W. Write it as a series expansion in W controlled by powers of omega. You'll get a series of equations like so, and you can solve them systematically. And if you solve them, you get these equations here. Again, you don't need to remember all the details, but the point is, once I identify W, I can calculate script A from here, and it comes out to be this expression here, okay? So I have written it after multiplying by the phase volume omega to power k, because I'm getting ready to do the integral. So this is in a form ready for integration. Notice that I start with a naught. I have corrections involving derivatives, and then there are more gauge fields involved here and so on. And then there is another series of terms involving u dot a, where u is this particular term here, okay? So therefore, what I need to do is to look at this series of terms and see what it looks like. Okay. Now, we can sum it up. And summed up version of that series is exactly what I'm giving here. So what I'm going to do is to take this script A, go back to this equation here, vary with respect to A naught. I'm going to get contributions from here when I vary, from here, from this dA naught, from here and so on. Look at all those terms, write it as the change in u star u, and here is my expression, okay? And I have summed up this series that I showed you here, and this is the expression I get. And then there is the second series coming from this set of terms here. Okay, it looks simple. The summed up version tells us that the difference between the u's with a changed background compared to the original background is d of something, which involves the u star u itself, and an expression q, which is given in this formula here, okay? So what is this q? Okay, I claim that that is a generalized Chern-Simons form, which connects to non-zero gauge potentials. Okay, so let me define what I mean by that. So this is following from the calculation I outlined already, but let me now define what a generalized Chern-Simons form is. Here is how we define that. We take an invariant polynomial. Remember, we are eventually going to use index densities as the invariant polynomials. So we have some invariant polynomial involving the curvatures, symmetrized trace of products of f's, and so on. This part is general, could apply with non-abelian backgrounds, whatever. We look at the difference of the two invariant polynomials with two different f's, f prime and f. And this difference can be written as d of something. And that something q, which depends on the connections for f prime and f, is given by this formula here. This is a product here. I put the commas because in more general cases, you may have a more general polynomial. But the first entry replies by a prime minus a. The others are f of t, where at is a linear interpolation between a and a prime. This is the old Chern trick in calculating Chern-Simons forms. So in terms of that, you can write this expression, and this Q here is called a generalized Chern-Simons form. Why is it generalized? Because if either A or A prime is 0, this is just the ordinary Chern-Simons form. Okay, and you might say if you write PF prime and PF as derivatives of Chern-Simons forms for A prime and A, then Q should be related to the difference of these two. But there might be additional exact terms which you miss because you're taking D of Q here. This formula for Q captures all that. Okay, so this is what I just finished saying, that the difference, I can relate Q to the difference of two Chern-Simons forms, but there is an additional term, and that is important for us, so we have to keep that, and that's what this formula captures. Okay, so this generalized Chern-Simons form, this is not the first time it makes an appearance in a physics context. It's known from the 1980s. If you try to define anomalies in gauge theories, but anomalies with a non-trivial background gauge field, then it is described in terms of this generalized Chern-Simons form. And that is a result that goes back to Matrices, and Zumino way back in the 1980s. Okay, so we're essentially coming back to that kind of term. Now, in the present case, if you take this A prime and A, which are related like so, take A prime to be little a plus A, namely the shifted background, A to be the unshifted background, just substitute into this formula here, and you get this result. Q is basically the Q that we found here. Okay, so what is the conclusion? That if I look at U star U, the difference between them is controlled by this generalized Chern-Simons form. Let's integrate from 0 to the equator, from the North Pole to the equator, 0 to 1, and write the expression for the lambdas which entered into the entanglement entropy. So the difference of the lambdas with the shifted background and the unshifted background, the difference is the integral of the Chern-Simons form, the generalized form. I normalize it now in terms of this integral with the standard volume measure. So there is a 1 over n. Capital N is little n plus 1, by the way. And there is this U star U in the unshifted background. And this is similarly the second set of terms that I have outlined here. This second set is done by a further power of omega inverse. So in powers of omega inverse is like 1 over n, an additional 1 over n power. So this is subdominant in that sense. Okay. The boundary I have shown here is really the entangling surface. It's a boundary of the region I integrate over, so it's the entangling surface. So what is the conclusion? The shift of lambda, change in lambda, is given by the integral of Q over the entangling surface. Now, the entanglement entropy is a function of lambda. So you vary lambda. This is the change in entanglement entropy. There is this factor, but there is delta lambda. So, and delta lambda must go like so. So we come to our first conclusion is that is what I show here as result 1, the leading field-dependent correction to the entanglement entropy is the generalized Chern-Simons term that I showed you. I have put in the spin connection here, and we will see that also emerging shortly, even though I didn't talk about it yet. Okay, so that's our first basic result. I'm going to look at it in a slightly more general context now. We want to generalize this to higher dimensions, non-abelian gauge fields, non-abelian backgrounds, gravitational backgrounds, and so on. So how do we do that? Okay, let me briefly talk a little bit about high-dimensional Hall effect, and then come to this similar statement, which is valid for all dimensions. Okay, so in high dimensions, we're going to consider CPK again. That's I can think of CPK, the complex projective space in k dimensions, as SUK plus 1 modular UK. So once again, this tells us that the curvatures of CPK will take values in the algebra of UK, which I can think of as U1 cross SUK at the algebra level. This means that we can have both abelian or U1 valued gauge fields and SUK background magnetic fields. Both are allowed, and we can look at states and Landau problem, Landau levels, everything with either type or both type of backgrounds. And what are the wave functions? similar to what we did for the sphere. There'll be functions on SUK plus 1, modulo certain well-defined transformation properties under UK. Similar to how we chose the right state with the R3 value, depending on the choice of the background, I have to fix the UK transformation property. Put another way, these wave functions will be sections of a UK bundle over CPK, and I can think of it that way as well. Okay. Now, each lambda level forms an irreducible SUK plus 1 representation. So they can be explicitly constructed and fairly straightforward to do. Again, the lowest lambda level will give me holomorphic ones. And more explicitly, they are again given by the matrix versions of the group element. The right states are fixed, the left states are free. And by the way, the freedom of the left state is what in the language of Holyfield is called magnetic translation symmetry. The left action is a symmetry of the problem. So let's take these wave functions. I don't need to construct them explicitly and show you all the details, but the point is there are these wave functions, but notice that there is an index on the right side because the states on the right side may transform as a non-trivial representation of SUK, so it's not necessarily one-dimensional. Okay. So therefore, when I try to define my occupancy matrix and a symbol associated with that by multiplying the matrix by the wave functions, I'll get a smaller matrix. So the symbol itself is a matrix valued function. And likewise, script A will also be matrix value, smaller than the matrix we started with, but nevertheless. Okay, and so let's look at this occupancy matrix. Look at the time evolution. It's given by unitary transformations on these states. It obeys some kind of a quantum Liouville equation. I can write it out as an action for, I can write an action for this equation. It reads like so here. If you vary U, you will get this quantum Liouville equation. These are still in terms of operators or matrices on the full set of states. I can write it in terms of the symbol, in which case I need to introduce star products. So this is my action at the level of symbols. Well, it's not difficult to see. This is a covariant derivative using script A as a connection along the time direction. Therefore, there is an obvious gauge symmetry here, which in the language of star products is this transformation here. Okay, so this is a gauge symmetry for the problem. But we know that if I have background gauge fields, the gauge symmetry is just the standard, usual run-of-the-mill gauge symmetry, namely delta A mu is some covariant derivative of some parameter lambda. And this is the full background plus perturbation connection. So this is the covariant derivative, and that's what I need. Okay. So what do? We want this transformation on the background to induce this operator level transformation so that I can implement the gauge symmetry at the level of this action. So that means I can choose script A as a function of these fields here, the backgrounds, and the lambda, the gauge parameter, also as a function of the original gauge parameter, capital lambda, and it may be a field-dependent gauge parameter now. And once I choose them as these functions, I demand that this transformation induces this transformation here. In that way, I can calculate script A. And if you do that, here is the series that starts off script A. Now this is for a full-fledged non-abelian high-dimensional case. Okay. And there are further terms which can be calculated. I don't display them here. And this is in a paper by Dimitra Karabli. She also shows that this is related to a generalized Seiberg-Witten map. Essentially, this construction of A is going to give you a Seiberg-Witten map for the problem. It's also possible to construct this by purely matrix methods. But either way, we know how to construct script A. And this is another way to calculate what I mentioned earlier. But I want to talk about something a little bit different here, which makes it even simpler. Remember, the lowest lambda level wave functions must obey some holomorphicity condition. So they are in the kernel of some anti-holomorphic operator. Now, how do we count this number of wave functions we have? There is an index theorem for that. The index theorem is naturally, because I'm looking at the kernel of an antiholomorphic derivative, will be naturally the Dolbeau index. So I can calculate the number of states, the bulk part of trace B, etc., by relating it to the Dolbeau index theorem. In particular, the index density is like a charge density for the problem or the occupation density for the problem. So it is in fact the sum of U star U. Therefore, I start with the Dolbeau index theorem. Here is the index density I have written out. The Dolbeau index theorem tells you that it is given by a Todd class on the complex tangent bundle times the Chern character. One doesn't need to know the general formula. I can write it out explicitly in terms of curvatures and the gauge fields in a series like so. Involves Chern classes and so on. And once I have this index density, associated to this index density, I can use my old trick, namely define a generalized Chern-Simons form. Take P of f prime minus P of f, where the invariant polynomial is given by this index density. Script f could be the field, the gauge field f, or the curvature r. And using that in a general way, I can define Q, the generalized Chern-Simons form. Okay. So for every index density, I can do that. In particular, for the Dolbeau index density, I do it here. Okay. If I do that, then it's easy enough to see from this argument that the index density works as a charge density or occupation density. We can actually calculate the quantity U star U that I want. By the way, using this index density, we can also integrate up to get an effective action, and that is written in a paper with Dimitra here. But we are not interested in integrating up to get the effective action in the 2k plus 1 dimension or whatever. We are interested in the entanglement entropy. So we are interested in the shift of U star U and its integral when I change the background fields. So the end result of this argument, therefore, similar to what we did before, is look at lambda with the shifted background minus, if you like, the unshifted background. Here, little omega is the spin connection. And the difference between them is the integral of the Chern-Simons form. And that Chern-Simons form is the generalized Chern-Simons form associated to the Dolbeau index, because that's what gives me the lowest level Landau wave functions. So once I have that, and these are the second series of terms that I showed you, I'm not going to go into details of that, but basically our claim is that the Dolbeau index density gives you a generalized Chern-Simons form, and therefore I can restate my result one in a more general framework, that the leading field-dependent correction to the entropy is the generalized Chern-Simons form associated to the Dolbeau index density. Okay, so that's a firm conclusion I can make. I have a few more minutes. I want to try and see if I can say something more. It's a bit technical. I'm not sure what physics I can draw from it, but let me show you something. I want to turn to another observation about entanglement now. So we talked about the modular operator. So we can calculate what this is for a given state. And we want to calculate it for the nu equal to 1 state. Okay. Now recall that the modular operator is related to the conjugation, the antilinear operator, Tomita operator S, which takes A to A diagonal like so. Now Witten's reviews a modern physics article from 2018. There's a very nice explanation of how to calculate this. I was actually going to go over that, but I don't know if I have time. Let me just take a look. So I'm going to skip over some of these details. What I want to show you is the following. I can define a delta for our nu equal to 1 state and calculate its spectrum. The way it works out is, a simple way, the result of Witten's analysis here is that one way to calculate the spectrum of the modular operator is you take your system, you define these reduced density matrices. Here there is the density matrix shown in some usual form in terms of Cat-and-Bra states. And these are the occupancies of the various states here. So these are reduced density matrices correspond to what you might call AO and AO prime. And then delta is related to rho 1 times rho 2 inverse in the split form of the Hilbert space here. And if I consider a general state phi, then delta, which depends on the starting state psi, but if it acts on a general state, I can write it in this form. That's a conclusion of Witten's analysis. I will not go through that in detail. But once I have this, we already have the reduced density matrices we talked about some time back. Here, in the Hall effect, I talked about reduced density matrices by in tracing over things outside, sorry, in the southern hemisphere and tracing over things in the northern hemisphere and so on. So I can calculate, therefore, what delta is from here. Okay.
So just to clarify, sorry, can I clarify?
Yeah. Go ahead, please.
This delta psi is the Tomita-Takaki operator?
Yes, indeed.
So
Okay.
you're calculating it in some detail here.
Yes. So I'm just taking that Tomita-Takasaki operator, and in the context of the Hall system where psi is my nu equal to 1 state, I'm calculating its action on a general state. And I'm going to find the eigenvalues from there and see what they look like. Okay, that's the idea. Okay. And this problem is simple enough that you can explicitly calculate delta and look for its eigenvalues.
Okay, thank you.
So once I have rho 1 and rho 2, which I showed you a moment ago, namely rho 1 corresponds to tracing over states in the southern hemisphere, the C operators that I showed you, and rho 2 corresponds to tracing over things in the northern hemisphere, which means tracing over the B operators I showed you. Now the inverse exists because one of the premises of the Tomita-Takasaki theorem is that you have a cyclic and separating states. Separating states guarantees that rho 2 inverse exists, that all the C's have to be non-zero. Okay. So therefore, I can now take a general state in a 2x2 matrix form again, in terms of the B's and the C's, right, in terms of arbitrary elements here. Okay, all I'm using here is the fact that phi is a Hermitian object. Alpha, beta are real numbers. Act on this, this formula here. It works out to be this statement in terms of alpha, beta, gamma, delta. So delta becomes in the 2x2, sorry, in this phi state, it becomes this matrix where X is lambda over 1 minus lambda. So you calculate the spectrum from here. We have to take the product over all such states, and therefore the spectrum is given by product of all these values possible in every possible way. Okay. So what do I need to understand about the spectrum? I want to ask what kind of spectrum this is as I take n becoming large. For that, I need to do an analysis of lambda s. So I look at small s. I already told you that lambda is almost 1. This is the asymptotic expression in 1 over n. It's very nearly 1 here. I go to large s. Lambda s is almost 0. That's this spot here. This is the transition region. The separation between lambdas is maximal in the transition region. In fact, maximizes around the middle of the transition region. So you can even ask, what is the separation between two nearby lambdas, like n over 2 and n over 2 plus 1? And you can calculate that by doing a standard steepest descent analysis, and you can show that it goes like 1 over square root of n. So what we find is that as n becomes large, the separations go to 0. You end up filling up this entire curve from 0 to 1. Every single value that you give me at large enough n, I can find a lambda says that it fits this, okay? Because the separations all go to 0. So here is the analytic formula, asymptotic formula. I've also checked it numerically. If you take n larger and larger, like 100, 150, 200, and so on, you see that the maximal separation keeps on coming down. You can check this. And therefore, we find, therefore, that the spectrum, because lambda takes all values from 0 to 1 in the end, this spectrum takes all values in R plus, okay? So the full spectrum of Delta, therefore, is R plus. We can do this for CPK as well. The asymptotic formula is a little bit different. You can also, instead of taking the equator, you can put a curve at any latitude you want, and the formula still holds true. This is the more general formula. Okay, so our second result, which is essentially a mathematical result, I think it is important eventually, but I do not know how to derive physics conclusion from it yet, is that all the splittings I can do in terms of different latitudes for these curves and so on, for the nu equal to 1, the spectrum of this modular operator is R plus. Okay. Recall that spectrum being R plus in the field theory, that's what told us that it's a type 3-1 von Neumann algebra. We're not quite saying that here because we are only looking at one state psi and we are analyzing the spectrum. Okay. The fully filled lambda level is what is relevant for non-commutative geometry. So somewhere along the line, this result may have some physics implication. I still don't know what it is yet. Okay. I believe I have 4 minutes. I want to quickly run over something. I mentioned to you that the entanglement entropy is related to the Chern-Simons form, and I want to refresh your memory or remind you why that is interesting for gravity. So let me just talk about this old beautiful argument by Jacobson, which is showing the thermodynamic relation between, thermodynamic way of understanding gravity. Basically, you take this delta QT, delta S formula, the the first law of thermodynamics formula. And the idea is to look at energy flow across all Rindler horizons. Okay, so you look at an accelerated observer. The trajectory in terms of some parameter S can be written like this. A is the invariant value for the acceleration. This is just standard trajectory for an accelerated observer. It's this hyperbola that I have shown here. Change S to S plus lambda, that's equivalent to a boost. And I can write it, the boost direction in this fashion. There's a null vector here multiplied by A lambda. Okay, just follows from this formula here. So you look at therefore inflow of energy through the horizon, and that inflow can be written in terms of the energy moment tensor times, of course, the area elements and so on, which I can write like so. Okay, so because of this boost, that determines the direction I'm going in, and that picks up a particular component of t multiplied by A. Now, we also have a change in the area that you can calculate. The change of area is what happens is because there is a horizon and there is an expansion of the horizon parameters, the area changes in this fashion as I change lambda or S. Here I'm changing S or lambda. I want it for small lambda actually. And the change or the expansion can be related to the Raychaudhuri equation, which tells you how theta, the expansion of the horizon parameters changes. That's a parameter that goes into the area here. And that's related to the component of the Ricci tensor. Okay, so for small lambda, I can integrate this to get this formula. Okay. So I know the change in area, and I can declare a la Bekenstein-Hawking that's a change in entropy. Now, I also know, because it's a Rindler horizon, I know the temperature, which is A over 2 pi. So we can put it all that into this formula here, and out follows just Einstein equation because I get Ricci tensor here, energy flow involves the energy moment tensor, and basically you get this equation. Okay, so Einstein equation can be obtained from the thermodynamic relation if you consider all possible Rindler horizons everywhere in space-time. Okay. Now the entanglement entropy. So what is used here is the Bekenstein-Hawking entropy, but it's also the entanglement entropy we know from the work of Ryu and Takayanagi and others. So basically what we are saying is the entanglement entropy, a la this argument, leads to Einstein-type equations, gravity. Okay. We also found in the Hall system, entanglement entropy is related to a Chern-Simons form. Also, if I model non-commutative geometry using the Hall system, then I'm claiming that the entanglement entropy relevant for that is related to a Chern-Simons form. So this suggests that Chern-Simons form and gravity should be related. And indeed, we know that in 2+1 dimensions, that is the case. Einstein gravity in 2+1 dimensions is the difference of two Chern-Simons forms. This is a well-known result going back to Chikara and Townsend. you have left and right SO2 gauge fields, spin connection, and the frame fields form one component, omega plus E, omega minus E is the other one. You look at this difference, it turns out to be Einstein action with a cosmological constant. Okay. And you can do this in high dimensions. In say 4+1, you can still take the difference of two Chern-Simons. The leading terms will be the cosmological constant term, the Einstein action, and then of course there'll be further powers of R that appear. Okay, so there's a whole class of Chern-Simons type gravities I can define for which the leading terms are the Einstein term with a cosmological constant. So putting all this together, what are we saying? Our result that the entanglement entropy is related to the Chern-Simons form gives a point of connection between Einstein equation as an equation of state related to entropy and thermodynamics, gravity as described by Chern-Simons theory, which is in 2+1 or even in high dimensions, gravity on non-commutative spaces using lowest Landau level of Hall effect as a model for such spaces. So there is a circle of ideas into which the calculation I showed you fits in. It's not all connected yet in a nice, neat fashion, but that's basically the take-home point that I want to leave with you. And thank you for your attention. Thank you.
Thank you. I should unmute and mute probably. Well, we can thank everyone. I'm not going to unmute everyone yet. We just take questions. We can thank Parameshwan at the end. So are there some questions? Yes, Marianne.
Okay, yes. Firstly, thank you for your talk. It was exceptionally clear as usual. My question concerns the relation of Hall effect and non-commutative geometry. In the old days, Kohn described the integral quantum Hall effect by non-commutative geometry, but I have not seen a convincing way to do it for the fraction quantum Hall effect. On the other hand, your approach is perfectly general, so it would be technically more complicated for the fraction one, but it should work.
It may work, but I have to confess, I have not looked at fractional quantum Hall effect in detail. And the main motivation for that is because, the main reason for that, if you like, is because it is the fully filled Landau level that really gives you a model for the non-commutative geometry. If I have a fractional occupancy, then it is like having a space in the end which has some holes in it, roughly speaking, which doesn't cover the full volume, so to speak. So I have not looked at it in detail. Now, on the other hand, the general analysis in terms of the index densities and things that I have outlined, many of those things will actually go through for a fractional Hall effect as well. So I believe the answer to your question is yes, there should be a way to use all these analyses for fractional Hall effect and make useful statements there, but I haven't quite proved any of that yet.
Thank you.
I cannot quite hear.
Yeah, I can't hear.
Can Domenico, you
yes,
wanted to ask a question?
Yeah,
Sorry.
yes.
I didn't realize I was muted.
No. Okay, sorry. Hi. So I have a couple of questions. So for me, I mean, the integer quantum Hall effect is described. So it's characterized by the Chern number. So yes. This is the topology usually that we know about the integer, the simplest one. So I was wondering. So my first question is exactly where in the calculation of your entanglement entropy, where the Chern number should appear. Somewhere, together with the Chern-Simons, right?
Yeah, let me answer that first before you get to the second question.
Yeah, yes.
The index density basically carries that information.
Mm-hmm.
Because, I showed you the Dolbeau index density. So the leading term, if you take, for example, the two-dimensional case, the leading term is the first Chern class.
Yes.
So that information is carried by the index density. There are, of course, gravitational terms as well in that formula if you go to a curved manifold.
Yes.
That gravitational term is also important in Hall effect. That is what corresponds to the Hall viscosity.
Yes. Yes.
Okay. So what I showed you generally when I go to high dimensions is a high dimensional generalization of both those things, namely the effect of the Chern numbers of the Chern classes, as well as the gravitational contributions. Okay.
Okay.
And you have a second question.
Yeah, yeah. The second question was related also to the previous one about the fractional quantum mole. So because usually in condensed matter physics, people calculate the topological entanglement entropy. So if I have a topological order, let's say fractional quantum mole, so the natural things for me is to calculate the topological entanglement entropy, and then I get a number. So it's not the area law like the Bekenstein-Hawking. It's just an additive term that gets from the topological order. I'm wondering if the connection, the possible relation to your approach.
Yeah. Okay. The topological, the number they calculate normally.
Yes.
Is not something that depends on the background. I mean, it is of course dependent on the choice of the background connection and so on, but it is not, we are not varying the background connection. The calculation is done for a fixed background.
Yes.
Therefore, you simply get a fixed number. Okay.
Yes.
That number is there if I calculate explicitly the entanglement entropy, which I didn't show you in this analysis here. But the paper I mentioned by Dimitra is actually doing that in higher dimensions. So there is a number that will come out, which is precisely the topological entanglement entropy number that you say. What I am focusing here, because I was interested from the point of view of non-commutative geometry, is to ask how does it change when I change the background fields. Okay, so that's a relationship. Okay, so the paper by Dimitra will contain the answer in high dimensions of what you just mentioned.
Okay, cool.
The two-dimensional case, of course, you know the answer it's already existing in the literature.
Yes. Yeah. Okay. Thank you.
Jay Grun.
Hi. This is more or less a bit irrelevant, maybe. At the end, you said you were talking about Chern-Simons gravities in odd dimensions.
Yes.
Is it included there the fact that all the lapse functions in all odd dimensions are the same function for all of them, namely ADS? Is this a well-known thing? I don't know.
You're talking of the lapse functions.
Yes,
Okay, I didn't go into the details of that. That is true. The Chern-Simons gravity, the action as I have defined, you can do in any dimension.
Yeah, in any odd dimension.
In any odd dimension, that's what I meant, sorry. And if you split into lapse and shift functions, the important thing about the lapse function is that so long as you're writing a topological term, I believe the lapse function can be shifted as you like. Okay, if you like, recall that the lapse function can be set to 1 if you like by using the Hamiltonian constraint of relativity. But here, effectively, you're looking at Chern-Simons-like forms. So I believe the lapse function can be taken to be arbitrary. And you can redefine it in all these cases.
Okay, thanks.
Val?
I have two clarifications.
Yeah.
Normally, the Chern number, let's consider H2, and
Yes.
standard Chern character is for a U1 line bundle, for a U1.
That is correct.
Here you have n levels, so it's actually a higher rank vector bundle on the 2-sphere, and at least I don't know any.
No, I don't have a rank vector bundle, Bal, for the 2-sphere. No, the n states are simply sections of the same U1 bundle, different sections. So it's a line bundle, and I'm looking at little n plus 1 different sections I can take.
But they are, in terms of wave functions, they're actually orthogonal.
That is indeed true. You could, in principle, define another connection on those wave functions, but that's not the one I am looking at. I'm only looking at a U1 background.
I'm a bit puzzled because so far as I know, okay, this kind of thing also happens in molecules. For example, the ethylene molecule, which we have discussed, or in actually in Yang-Mills series, okay, where you get higher rank vector bundles. Okay, so at least you can interpret it in two ways. One is as a say different sec. I don't know about this interpretation with different sections, but as higher rank bundles, okay, this has turned up in Yang-Mills context also. Okay, so okay, so your answer is you're thinking of it in a different way.
Yeah, let me say one more thing which might clarify it, right? Is that if I look at these wave functions I wrote, and I try to construct something like a Berry connection, that would correspond to in principle, a non-abelian gauge field. And that's the one I believe that you're thinking of. What I am doing is to think of all these wave functions as different sections of a given U1 bundle. So the bundle is just one-dimensional. So these are two different things, I think. I'm not talking of the latter. So if I were to look at adiabatic flow of wave functions on some larger space, no, sorry, even on the two-sphere, if I think of adiabatic flow over a certain set of parameters, I would encounter something like the Berry connection, which would then relate to what you are saying, I believe.
Okay, let me ask a related question. Okay. Suppose I give you a line bundle. Okay, does it allow, or how many sections does it allow of wave functions in the Hilbert space which are linearly independent?
Well,
cannot be arbitrary, no?
No, but in this particular case, we know the answer, right? Because we are looking at the lowest lambda level. That number is counted by an index theorem, and that tells you exactly how many independent sections you can have. Right, because
yeah, I see. The Chern number gives you the difference. Okay, fine.
Exactly.
I see. What is your cyclic and separating state?
Well, the claim I would like to make is that the nu equal to 1 from the analysis I showed you qualifies as a cyclic and separating state. The completely occupied lowest lambda qualifies as a cyclic and separating state. That's my claim.
Finally,
yes,
if I have followed you correctly, you're actually also proving that this is hyperfinite. Proving means at least you're going in that direction. You're taking limits of matrix algebra.
That's correct.
So the only thing, there are technical issues of whether it is an appropriate inductive limit and so forth.
Exactly.
But now, then the claim will be that this is, but there is only, as you know, there is only one type of hyperfinite type 3-1. There is only one algebra like that.
I agree with that.
So,
yes.
So it is the same as quantum field theory.
I don't know. That last statement I am not yet ready to make. All I'm saying is that there is the spectrum is R plus. It is going in the direction of hyperfinite type 3-1. I don't quite know what the implications are because I'm only looking at one completely occupied lambda level state.
That this corresponds to the limit of infinite magnetic field.
Yes, indeed. Indeed.
So maybe it is, I don't know.
So there is something interesting there, I believe, even though it's a technical statement. But at the moment, I'm still not able to draw any firm physics conclusion from it. Actually.
Ricardo?
Oh God, too many questions.
Okay.
Let me start from the end. Chern-Simons
yes.
has no dynamics.
That's right.
Or to call it gravity, I think is... yet, what I found very interesting in your talk was this characterization of, it reminded me of Bogoliubov transformation between inside and outside, which is a language I learned at Maryland.
Yes, indeed. in that context, let me just make one quick remark.
Hmm.
The relation between inside and outside, the Bogoliubov transformation, you're of course familiar, that turns up in the black hole context as well. And
Yeah, that relates to the work of this guy, what's his name, Jacobson? I met him sometime.
yeah.
We was playing guitar.
Oh, okay.
But the other thing that I think is more relevant is
Yes.
your cue
Yes.
from your transparencies.
Yeah. Do you want me to go?
Another current, because from that you get physics almost immediately.
That's right. You can think of
It's like a stress. It's, well, within it a stress tensor.
I'm not quite sure I followed that last part.
From
the
another current, if you associate it with translations or rotations within the appropriate group that you choose.
Yes, I can define a current associated with
the same thing. The index is pretty much the second variation of the action.
Yes. So from the index, I can define a current. And one of the things you can do is to ask.
No, the current, you get it from the boundary term. That's what you introduced in your generalized.
From the cube, yes. But if you change magnetic fields, you also get a bulk response, which is given by the index density. And if I use that as a current, I can integrate up to get an effective action also.
Yeah, your reference to Moser's lemma was quite appropriate.
Yeah, well, that's that. I
I'm
thought
a fan.
it's almost a classical problem, right? When you phrase it that way.
All right, thank you for a very nice talk.
Thank you.
Marianne
Yeah.
and Werner?
Yeah, just a mathematical remark concerning Spahn's first question. They proved that on the two-sphere, all holomorphic vector bundles split into line bundles. So Palmer-Schwann's approach is perfectly adequate.
Okay, thank you.
Okay, thank you. Brian, I think you had a question, but you've read low.
Well, it's kind of historical now, but it relates to Tigran's question again. These wave functions that Palmer-Schwann writes down, the n+1 of them with s running from 0 to n, they're actually zero modes of the Dirac operator.
Yeah.
So they all correspond to zero energy, and the ground state energy is degenerate.
Mm-hmm.
And the general ground state wave function is only a combination of these n+1 zero modes. So it's not an on-abelian UN you've got in there. They're just all different sections of a U1 line bundle, but they're linear independent.
Yes.
I didn't mention the Dirac operator, Brian. I should. But I also mentioned CPK.
Yes.
And as you know from, or as I know from your paper, CPK, we had to put a spin C structure to count the zero modes of the Dirac operator. If you do that, then of course it agrees with what I'm talking about here.
Yeah.
Okay.
And Bal, you have another question.
Just what did Werner say? I could not hear very clearly. Maybe you can repeat. It comes muffled.
Okay, on the sphere, on CP1, every holomorphic vector bundle splits into line bundles.
Yes. Okay, I see. Okay, thanks. Can you make one remark which may be helpful? The idea of looking at the Dirac operator, like Brian suggested, is that actually you're looking at the ground state of a Dirac operator. Another way of saying it, no?
Right.
It has been used, and they form a representation of some. In this case, I mean, you can think of it as forming a representation of some group, the set of zero energy levels. Okay.
Mm-hmm.
I know that this idea has been used for analyzing representations of the Lorentz group by looking at the Dirac operator on hyperbolic manifolds. Okay? There is a rather extensive literature, I believe, literature on this. And I was told by Narasimhan that there is this work done by somebody in TIFR. Okay? This may be useful.
Okay.
Literature exists. Okay?
That'll be very useful. Yes. Thank you.
Okay, Charles, you have a question? You're silent.
Yeah, I'm unable to hear.
Okay. Can you hear now?
Yes, yes.
Yeah. Just on the question of bundles on in 2 dimensions, and the Dirac and the holomorphic operator, the Dirac operator and the D-bar operator are essentially the same thing.
Yeah.
In 2 dimensions.
Yeah, indeed.
Yeah, yeah.
Okay, I think we have exhausted the questions. So let's thank Parameshwaran. I'm going to unmute everyone. So we'll see how it works.
Thank you. Thank
Very
you all.
nice talk.
Thank you for very clear and nice talk. And the recording of it should be on our website before too long. I'm going to pause recording at this point.
Okay.
Stop recording.
So thank you all. And